All right. So in this class, I want us to quickly check the applications that we will need whenever you are to consider a Zener diode. Remember, you also need to understand the calculations as it is to consider that same Zener diode. We have got this part of our regulation. If you still remember that when we had the part of a rectifier, let us just say consider to say we've got a rectifier circuit, okay, that is going to be a full wave. So this can be a full wave. It can also be a half wave rectifier that we are having in this case. All right. So let us just say we have got something of this nature where this is to be considered as either a half wave or it can be a full wave. So here we can just consider to have a half or a full wave. That's a rectifier in that case. So with this rectifier, as we do understand that we are going to be having the output from it. And that output is not regulated. So the output that is here, output from the rectifier is the one that we are to consider. It is the output from the rectifier. All right. So with this output, it is not regulated. We've got a voltage there that is not regulated. So the application now of this Zener diode is to regulate this output that we had from our rectifier, meaning to say a half wave or a full wave. You now have to regulate this. So this one is actually unregulated. Talking of an unregulated voltage. So the application now of this Zener diode is to regulate this so that it can be a regulated voltage. So that is the major application that we are going to actually consider on these calculations of our Zener diode. So this is considered as a Zener, that is as a voltage regulator, as a voltage regulator. So considering a Zener diode to regulate output of a rectifier. So this is what we have now. This circuit, remember it is from the rectifier. It was the output, yes. But now as it enters the circuit of the regulation, because we are supposed to regulate here. So as it enters, now it's considered as V in. It was the output that we had from the rectifier, but as it enters this other combination, because it's another circuit, this one. It's a different circuit that you're going to have. So it's only that you have this before you consider working with the rectifiers on their own. But this is what you're going to have, guys. I think from N3 had these rectifiers. It's now an input. So this is the one that we're going to have here as our input. So we're just going to have now the part of the rectification. I mean, the regulation part now. The rectification is done. Now into the regulation, we're going to have the series resistor that is connected to the Zener diode. So that is your Zener in that case. So this is the Zener diode will be in parallel to the load. So as the voltage is now regulated, it is now going to the load. And to the load, that is where we have got our load resistor. So that is the combination. So this one, it was supposed to be a circuit on its own, guys. Remember that part of your full wave is it you're considering the 2 diodes or 4 diodes there. The output from there is the one that I'm considering to say it is not regulated. It is unregulated. So that output becomes the input of the regulation circuit now that we have here. So it becomes the input. This is the output that it becomes the input, which is our Vn And that Vn that we are considering is unregulated for this one. It's unregulated DC. So this one is unregulated. That's unregulated DC voltage. Which is what? The output that we had from the rectifier there. This is your input that is entering to the what? To the series resistor. So this is RS, the series resistor. The diode, so you're just going to consider DZ, and the load resistor. This is our RL. As it is on the load resistor after this diode, because the diode is there for the regulation purpose, it means the voltage that we are going to have at the output in this case, the voltage that we are going to have at the output, which is our V out, the voltage across the load resistor, as we can see, is since these are in parallel, it is the same voltage as here, which is the voltage of what? Of the Zener, okay? The voltage across the Zener diode here. You can see that it is simply the same magnitude of voltage here. The voltage across the Zener diode. It is equal to this output. So this output voltage is the regulated voltage. So now you're talking of the regulated now output. So that is the condition there. Regulated output voltage, which is our V out. So you can just consider maybe there's points A and B at the output where the load resistor is connected. Okay. Across this resistor, we also have the resistance. As the current is flowing, we are going to have a voltage drop. As the current is flowing from the supply, the current is going to flow in this direction. This is the current entering. This is the current from the supply. So let's say this is the current across the resistor. Since we've got a resistor there, a series resistor, so we're going to call it IRS for the series resistor. So this current creates a voltage drop. As there is a resistance there, we are going to have what? A voltage drop there, which is VRS across the series resistor caused by the current. This current, it enters, was it is from the supply. So it's going to enter at this point. Remember your Kirchhoffs? The current that we had at the supply, another one enters here. That's a current. Another one extended to this other branch. So they are taken from IRS, the supply. Another one is entering here in the diode, our Zener diode. So this is the current across what? Across the Zener diode. The current that is going to be at the output across the load resistor, that is the current across the load, which is the same current here flowing to this point, which is the current across what? Across the load resistor, IL. So with the understanding of this diagram that we are seeing here, we can have some formulas taken from this diagram. We can have some formulas taken from this diagram. Okay, let us just have our calculations and see how it is going to be like here. So on our calculations, we can see, considering the currents, considering these currents, we can see that from our Kirchhoffs, the supply there, IRS, so that is the current across the series resistor, is going to be equal to the sum of these two. It is the one that is supplying the current across the Zener and also the current across the load resistor. So that means we are talking about the series current through R, the current through the series resistor. That is the current across the series resistor there. It's going to be the sum. So whatever that you want, you can make this the subject. You can make this depending on the question. Okay. In terms of the resistance value here, in terms of RS, if I have got this value and I've got this value voltage, I can find anything there. So it also follows that RS, which is the series resistor, is the voltage that we have across the series resistor. This one, the voltage that exactly across the series resistor over what? The current across the series resistor. But let's think about this, guys, to say, let's go back to our voltage drop condition, because Vn is the supply and there is a voltage drop across the Zener, which is equivalent to the output voltage. Remember, like I said, V out is equal to Vz in parallel. Okay, that is for a parallel combination. So here I'm saying this circuit here, that here, this combination where we have got the Vn, the VRS, and the voltage across the Zener, we can calculate or have the voltage that is VRS, this one. We can have our VRS from the difference between these two. The one that is in between this VRS. It is the difference. VRS, the voltage that is across the series resistor, can be obtained from the difference between the input and the voltage across the Zener diode. So, guys, here they can give you even the power across the Zener. What you need is the voltage. You can use the current, power, whatever that you have. You calculate your voltage. Maybe you're not given for you to calculate VRS. So, let us analyze these two. This is about the series resistor here. Series resistor. So whenever you're talking of this RS here, the series resistor. Okay, our series resistor. So this is it. If we are to consider this now to say, if truly that VRS is equal to Vn minus Vz, therefore, this formula can also be written as, instead of writing it as VRS over IRS like this, because there is equivalent of this, which is Vn minus Vz over what? If there is an equivalent for this IRS, which is the sum of these two, therefore, we can present it with those currents instead. So it is going to be given as Iz plus IL, the current across the load. That is representing IRS. It is equal to the sum of these two. So instead, we can present our formula this way instead of this way. So you can present your formula in any way. That is for the resistance of what? The series resistor. This is the resistance of the series resistor. So that is where we end up with our formula. From the current and that voltage across the series resistor. So you need to understand all this. All right, let's talk about the output. We're talking about the input, about the series resistor. What about at the output there? At the output, we are going to notice that at output, okay, let me just write here, at the output. At the output, you're going to notice that that is where we have our V out, and that V out, remember I said it is equal to Vz, the voltage across the Zener diode, since these two are in parallel. So if that is the case, it follows that with that voltage, maybe might be given this voltage, you take it as your output. There is current, there is resistance. So what does it also tells us about the same voltage? It tells us that this same voltage at the output is equivalent to the current times resistance. That is the current across the load times the resistance across the load. So from there, you can calculate whatever that you want here. Is it the current? Is it the resistance across the load? It's just going to be V out over what? Over the current across the load, where V out is same as what? Is same as VZ. So it depends with the condition that you have. But at the output, mainly, they'll ask you about those resistance, maybe current, whatever that you can have. You can even calculate the currents from there. Remember our Kirchhoff's law from IRS is equal to IZ plus IL. We can go back there and calculate IL from there if it is not given. So it depends with the condition. So these are calculations. It depends with what are you given, which formula to use. Also, they might even ask you questions back here to the Zener diode. It's not like you're going to be given the currents direct or the voltage direct. Sometimes they might not give you the current. They will give you the voltage across the Zener diode and the power across the Zener diode. So you must consider also that part of a Zener diode, okay? So across the Zener diode, let's just see what's going to happen here. Just across the Zener diode. So across the Zener diode, one thing that we already understand is on the voltages, the voltage across the Zener diode. That is one thing that we have already. The voltage across the Zener, we said, is equal to the output. So there, we're going to consider that also. This part of IZ, we can calculate that current from what? Kirchhoff's. Take this current to the other side, you can calculate that current. Sometimes you're given the power. So if you are given the power across the Zener diode, that power is equivalent to the maximum current times the voltage across the Zener diode. That's current across the Zener diode, this one, which is simply equivalent to IZ times VZ. So from there, they can ask you to calculate the maximum current. So it's simply going to be power over voltage. That's you've got what? The current. This is across the Zener diode. So as you consider these calculations, it will be very, very important to see which part are you considering. Are you talking of the part across the series resistor? Are you at the output of the circuit? Are you considering across the Zener diode? So you must consider that in your calculations. And also, this same diagram that we are seeing here, this series parallel combination, they can actually confuse us with the diagram in the same way like this. So this diagram, we could have drawn it this way of a voltage regulator from that unregulated DC supply that we have. So we're going to have it this way. So I'm just going to have, remember, it's a series parallel. So you're going to have the series resistor here. They can draw it this way. Okay, then the parallel combination now. So you're going to have this in parallel. So let's just save it this way. So this is the input. Here, there we are at the input. So this is our Vn, which is that unregulated. Then there we are going to have now the Zener diode. Okay, so you're going to have our Zener diode in parallel with what? The load resistor. Still, that's a series parallel combination. We still have series parallel combination at the output there. So that is, you're going to have V out at these terminals. At these terminals, that is the V in, which is that unregulated voltage. Remember, the unregulated. DC voltage. So with the Vin, this is our series resistor. This is our load resistor, and that is our Zener diode. The current flowing from the supply is our current that is going to be affecting the series resistor as it is. So this is going to be called the current across the series resistor. This current branches at this point. Another one to this branch, another one in this branch. Separated, that makes this to be parallel. So another current is going to be this side, another current is going to be entering this side in the Zener, another current going to the what? To the load. So this, and the rest of this current is the one that is entering what? The one that is entering the load here, which will give us the output voltage, which we can see that this output voltage is the voltage across the load resistor. It is the same voltage across the Zener diode. So with this, we are going to obtain a voltage drop here across the Zener diode. There is a voltage drop. That's going to be VZ across the Zener, which is exactly the same of the same magnitude with V out. So that is, they are the same. Across the series resistor, because there's a current that is flowing and there is a resistance there, we are going to obtain a voltage across the series resistor. So with this, we can even tell that Vn is the sum of these two. Vn is the sum of these two, VRS and VZ. So VRS, which is the voltage across the series, that can be calculated by manipulating our formula. It will be Vn minus Vz is equal to VRS, which is, we are back to those formulas. VRS is equal to Vn minus Vz. The current IRS is the one that is supplying IZ, also supplying IL. So it follows that IRS is equal to IZ plus IL. Same calculations that we had are going to be formulated from this diagram. So it's, I don't know which diagram do you understand better, but they can give you a diagram presented like this is still the same thing, series parallel combination. So it's the same thing here, the series parallel, just that this is written on top like that. That is the same thing. So these are the calculations that I need you to go through, understand this, as we are going to have examples in our next class. We are going to be now working with questions that can be either for this type, okay, like presented this way. It's the same diagram like that, guys. I'm just saying the presentation. I don't know which presentation. Do you understand better? Do you understand it that way? Or do you understand it from the other one? But that is the condition of what? Of the voltage regulation. And as I said, at the output, this voltage will be what? Will be regulated. This is, so there we have got a regulated, and in parallel, the voltages will be the same. Vz will be equal to V out because we're referring to a parallel combination. So let's try to grasp the concept so that when we are going to work out with the questions, you'll be understanding what is happening in terms of the calculations. These are the major calculations that you actually need. Till we meet again.